Is there? Yeah, we can start. Okay, anybody? I think now we are ready to start.
I guess now you're not gonna draw.
Great, so let's get one. So for today's this week's stream seminar, we're very happy to have Marija Tomasevic, who will tell us about how to dress up naked singularities.
Yes, thank you. Thank you so much for inviting me to be here. It's always super nice to be in Berkeley. Yeah, I'm going to be telling you about some work that I've done with my wonderful collaborator, Chikon Wu, who is now a postdoc in Washington with Marija Tomasevic. And yeah, it's on dressing up naked singularities. So, let me start by addressing the obvious. What is it that I'm talking about here? Are naked singularities? In order to answer that question, I have to just make sure that we're all on the same page when it comes to singularities in general. By singularities in general, I just mean any curvatures with values which are beyond the cut-off scale of our gravitational units, so for instance, one scale or a string scale. Naked singularities then, one with what one means by that is space-time curvature singularities which are not covered by any sort of a macroscopic horizon. Macroscopic meaning that the size of the horizon is bigger than obviously. Okay. So naked singularities by definition will buy what we call a weak positive censorship, which basically states that as observers can only see regular singularities. So they're not seeing singularities. That's the projection allowed to see regular. So if you do have naked singularities, they would then represent regions of some sort of low quantum gravity. As observers, simple, just go over there, and just experiments and get on. So the next question is then, do these singularities actually seem sort of relevant to the question of gravity? And it turns out that they are ubiquitous in nature, several ways than one can obtain, and are in some sense natural. So the most natural thing, similarities would be to simply take a black hole. You start with n black hole, and eventually it will shrink down scale, which is obviously not covered by macroscopic horizon. It will then represent for us in black hole events. Another way to obtain them would go one dimension higher than the usual ones, so 5 dimensions and higher, and take extended black objects, such as black strings. We can simply perturb such strings and turn them in a appropriate way. These strings would then wall, and they would eventually pinch off. And then where the string pinches up, this is the moment when we would create an shrink down the size, splitting off into separate parts. And this of pinching is called gradualized. Finally, one can simply do fine-tuning in order to obtain zero holes. So what do I mean? One can take stars with just an mass and collapse such stars. What will be a zero number, a very tiny number. So if you have a larger size star, you will collapse it, you break a black hole. If you have it smaller, it will simply disperse into one space. This is the critical set parameters which would be a very small. This collapsing into such tiny things is known as critical collapse. Okay. So in this talk, I'm going to be focusing only on this critical collapse. Operation endpoint and very opportunity that one can tackle by having to add extra effects, not quantum string effects, in order to see how these string effects actually modify similar nature of these other two models. But in this talk, we're going to only focus on the third ones. And if you're interested about what I mean by instructions, you just put less.
What's Q in this line?
That's a mistake. Alright.
When you spin the know what the collapses are.
Yes, this is the whole topic. Okay, so as I mentioned, any single clarifications from we're directly probing such regimes. I'm sorry. So what we're gonna do is just see how perturbable gravity affect the solutions of spherical gravitational collapses. So that's gonna be the central.
Sorry, I'm missing this, but like here we're talking about fluctuations at set possible level, or these critical class, like boundary, sorry, or sparsely.
I'm gonna now talk about it.
It's a large curvature region. Why is particularly quantum gravity something you look at?
Well, first of all, because this that you can do.
Okay.
Second of all, I'll show actually why higher loops are not gonna be affecting the main conclusion.
Okay.
I'm gonna also, I'll explain some of these features, but there are of course consequences.
Okay.
Okay, so with that said, we're gonna see what is this class collapse. Okay. And of course, I'm just gonna tell you some basic facts about it. There's a very nice review every couple of comes out by good luck, and it came out, and I do encourage you to take a look at it. But the classic area of critical collapse started with Tomasevic, who basically didn't not keen on like taking some spherical solutions or anything, just playing around mass scalars and basically seeing that he observed sort of phenomenologically some of the features of the So what did he do? So what Tomasevic did was to take some sort of parameter family, smooth initial data, asymptotically flat, everything very nice, otherwise. And so this one parameter family will have some which will evolve into a black hole spacetime, and some of the other members will evolve into just things. And other the family can be generic. So for instance, just to be concrete, we can take the profile for the scalar, which is gonna have some sort of profile. And now this Gaussian is setting the amplitude of this data. And first we take this scalar, we evolve it with a couple of equations, and then we find different solutions for different keys. It's a very low echelon. Now, some sort of notational remark here. We can always find the smallest p for which the black form, and we call such p star. So for p star, we're going to have black.
The mass of the scale. Sigma zero.
CERN, you can see several phenomena that justify the name why we call this critical collapse. And the key observation that led to this is the fact that near a black hole threshold, formation threshold, Chopsworth couples with arbitrarily small created, and the masses actually seem to have a schema. So all of the masses that you have that are very near this sort of grid, that have your masses scale with this gamma is sort of a number called the critical exponent. The reason why this is sort of called the critical exponent in the first place is because this gamma is completely universal with respect to the initial. So let's just think about that for a second. So this gamma depends at all on what type of external. It's always going to number. What it does depend on is just the type of the collapse matter that I have. So in this case, I have a massive scalar for any type of B, the gamma is going to be the same. It has another type of matter, gamma with a different number, but it will still be universal with respect to the speed for the same matter. Note that in quantum, this B sum is universal. It's going to depend on the Gaussian and depend on the actual profile. So all this stuff over here, then defined, but generic. So we see that it's fine-tuned, but we really have to sort of fine-tune to be, we fine-tune our P to be close to 1. So we're fine-tuning our initial data in order to close to this black hole threshold. However, it's generic because this is something that you observe in all types of matter. So for any matter that you're with, there's always going to exist some sort of a key star, which there's going to be a building block for these samples. Does that make sense?
It's 3D with also with respect to the initial data, but a little bit of mass.
But here I started with a master scalar, and this indicator out here is really it's massless. But when you introduce, then it's going to depend on whether this mass is dynamically relevant or irrelevant. And we're going to put this in this class.
I assume that people thought about like simple quantum corrections, like the range of the center of mass for accelerated collapse. Is that, can you be in a regime where that matter? Like you would want it to spread out more than the initial size of the black hole, for example.
Right, that's intuitively all very good. Quantum corrections, as far as I know, have been properly accounted for nowadays. So people have considered the quantum studying like what will be the actual width, which is a critical surface prices. Only the level, but not at the level of any sort of calculation. Before is also studying split states, critical constant effects, and there are other ways that people were trying to obtain this critical collapse, but all giving various results, and we have a whole section in our paper which sort of summarizes all these other papers. But what we're gonna do is try to be methodological about sort of try to make things.
Sorry, by quantum effects here, you mean both like where the matter is quantum, and so I guess you say have some kind of wave that is has some spread during the collapse, but also you need some gravitational effects too, or
Well, I am not taking into account any quantum gravity. It's just gonna be for in a sense of it's not gravitons, but it's just matter that you're gonna see. But for now, this is just a
okay.
also sort of any. Just want to make this point that yes, it's fine, but it's different.
Is there some explanation for this?
Excellent. There is. Here comes the explanation. So, the explanation is really going to be an intuitive for what the phase distribution. How do we understand this thing? So what have I done here? So here we have basically the base space, and then at each point represents the initial data set. So sets of spatial metric, and scalar, exchange curvature, and matter with constraints and so forth. So these write all those details. And the arrows, these blue and the red arrows, they are solution curves. So how does evolution basically take my solution? So in this particular example, mass scalar, we have split into two halves where one of the halves goes to the black hole, fixed point, and then the other one goes to fixed point. That's what I'm saying. You can matter to the black hole or not. And there exists exactly one sort of a curve in between, which has this sort of an attracting, which has a critical point, which is this one. This is the point.
This axis.
It's a cartoon representing phase space. This axis represents that. It's just yes, it's points. Many directions. It's just nice to draw. So the fact that you can go either this way or that way is also something visible from the linear perturbation theory, and this is how we saw that this is really what's going on. Perturbed slightly away from the critical point, there exists only one unstable point. And this unstable point is the mode that takes the flat space where the black is. And that's the case. So attracting like one direction.
The axis that you anything there are arrows into the
So on the surface itself,
yeah, so
if you start on the surface, then you're gonna end up in the critical point.
there's only one critical point in the light of field. So like for example, if I take the width of the Gaussian, would I end up at the same?
I'm not sure. I check that. But for sure, like if you fix this, So for doesn't depend. So the way.
Yeah, but I'm not able to like, the solution also.
Yeah, I should check that a little bit. For sure, and this will look for you.
Yeah, like it's space naively, I feel like you change the key, the sound, and then grab hold, things won't change. It's different times.
It's gonna be a different mass. Yeah, this is, as I said, this is a current,
Let's
it's
look at
a
it,
current
right?
picture of just like to imagine what is it doing, where either blocks into black hole.
But it's always said that regionalization is better at this point, and nothing moves. And it approaches, but here it looks like five or six.
Yeah, that's the end,
Yeah.
on the day of the pen.
There's some similarity with which.
Correct. Okay, so just to explain where does this scaling and universality come from? Well, we can see that by just these trajectories of the solution curves. So any sort of a trajectory that begins close to this critic to be equal to T star, but not exactly, is going to move very close to the surface and move away from this critical point. And so in some sense, you get the critical, near the critical point, it slows down a bit, moves away from the point. And it's exactly this behavior where all of these which are nearby the critical surface, they all go towards the critical point and then move away. This is the origin of universality. So why this mass scale is P minus P star to gamma? Because the only thing that you both here is that we do not care about any of the initial data, we really just care about this line of threshold. Does that make sense? Okay. Good. So I told you about the general spherical class, but there are types of discrepancies. So I drew one, okay, but it can have actually like two, which I'm gonna call type 1 and type 2. Type 2. So in the type 2, this is where this mass scaling law of value actually appears. In that case, the critical solution is known as a self-similar solution. What does self-similar here mean? Self means either that the discrete is self-similar or self-similar. Discrete giving some sort of Penrose diagram like this. Continuous would give something like this. Is this anything to you? Well, let me explain. So self-similarity here refers to the fact that the things that are called in way are going to look the same. And then like the metric here is going to look the same as the metric here, this spatial metric, and I'm scaling interval parameter towards the middle here. So discrete means that it's separate, like periodically separate until like hit the singularity. Continuously self-similar means that it's going to be looking the same all down. Right? So the solution repeats itself. And crucially, as we already in this type case, there is no mass scale. So I can reach up to small length scales, and of course, I can reach singularity, which has a zero mass. So just take all these masses, I both go at P minus P star, so I can actually reach zero mass solution by equal to P star.
Just one clarification. In the base diagram from the previous picture, it seemed like sort of like an unstable at the very center, but P is exactly P star, but it doesn't flow to a black hole at this point. Is that am I interpreting that?
Sorry, there's an unstable one?
Yeah, that there's like some unstable point in the center where if you set P exactly equal to P star, that does not correspond to a black hole. Is that correct?
So black hole is here.
Yeah.
Black hole solution line is here, and this is the naked singularity.
I see.
So P equals to P means that my mass is equal to 0. Right?
So it's sort of like a continuous method as I take my initial point. Okay.
And that's the reason also why.
Yes.
The reason why I call it type 2.
I see.
Okay, so that was type 2.
Mass because you have, like this solution had some energy about the value. Mass is just within the accuracy.
Well, mass of the scale.
Yeah, but.
And then I just
you
put
mean
some
mass? Or what do you mean mass velocity? Mass?
I mean, little action, I have a mass. There is no potential for this scale, there's only the kinetic. This is what I'm talking about.
I thought you were saying that the critical part of the mass is zero.
Sorry, the mass, yeah. Well, maybe. So I'm showing you the scaling law. This is the mass of the black hole, you're forming at the end of the day.
Okay, it's not really the local difference.
What's the black hole, so I guess you can measure it through it.
You have some contribution to the MS that comes from the scalar. Not all the scalars that they didn't go into.
Yeah.
No.
Okay, so some locally for the other.
I also think that there is like have equal to m or Schwarzschild times this factor with minus b star. This provided the actual scale. So you wouldn't create anything that is just something. Schwarzschild would create an actual differential classes. Okay. So that was type. There is also type 1. The type 1 solution is a little bit funny. So this type 1 refers to surface erosion. Okay? So the surface in the type 2 was self-similar. The surface type 1 is not so. It's time periodic. This also means that this solution is not going to be representing a zero mass solution at the end of the day, but it's going to have sort of a finite size. So the configuration, which is, you should think about it as sort of an unstable star, sort of a solid. So, yeah.
Why do you call it metastable?
Well,
Isn't it just unstable because it has an unstable direction?
Yeah, it has a unstable direction, so it's the least unstable.
But it's not long, it's not long lived in that makes sense, right?
Yeah, I would expect not. I think these solutions have been studied in so much detail. They're sort of maybe shown with some sort of configurations or something, but of course you do it to decay. Right? But the whole point was just to say that here your surface is type 1, you can never reach an integral actually. You always reach some finite size, which then maybe it's stable. It doesn't allow you to zero mass. And this can then be rephrased, but that's a finite size. There is an actual mass that's actually smaller scales. Okay, so those are the two types of surfaces that we're going to see.
So what determines the difference? I mean, like whether it's type 1 or type 2. Like talking about it as if it was always going to be the other one, right? You can determine small particles.
Right. The mass scaling law that we're talking about is specifically can reach an singularity, so that it's always type 2. The mass scaling law. Here, I will not have a mass scaling law, but I will have a different scaling law, which is why this belongs in sort of a critical solution. And the scaling law is going to be for the I guess time the time what do I call this all this unstable solid.
You gave a specific example from the master scale, the Gaussian profile.
Yeah.
That was the other.
Yes, exactly.
What would be a specific for this?
So I'm gonna show you. There's a specific example we're moving for instance. It's also not very obvious that if you have your Lagrangian a mass or some sort of potential for your matter, obviously you're gonna end up with a type 1 solution. You actually have to do the analysis in order to see what's going to happen. The reason why is because this mass parameter has to be a dynamically relevant scale in order to make a difference at these small scales. If it's dynamically irrelevant, like it's going to constant, then as you zoom in scales, you sort of wash out this other greater scale, and so you go. So just because you start with the Lagrangian, it doesn't mean that you're necessarily going to end up with that. And that's necessary.
So I'm missing obviously why do you care about these launches? You say don't have any singularities.
All because I'm going to show the two appear. They will appear. I'm just introducing some notion.
You mean they? I mean, you tell us the punchline.
Let me hear the punchline. The punchline is that if you take into account quantum effects, you will not obtain a type 2 solution, you will obtain type 1 instead. Quantum modified. So it's not like this, but it's going to happen.
So that's the
But the reason why we
That quantum effects make that one, and so they're not negative there.
killing the
Going back to the earlier slide, the singularity dot there.
Create them generically in classical ways, cycle evaporation, but you should also take into account other effects. That's the some punchline. Okay. So let me just like tell you a little bit about this, like why do we call them type 1 and type 1 and type 2? Because there is a sort of an analogy with phase physics. Where the black hole mass can lose its parameter. Type 1, if there is a mass gap, is then akin to the transition, because we jump from black holes smooth to the solution, but we have to take the finite gap and then jump. Whereas in quantum 2 actually for continuous scaling into the black hole 0, and so you can cross together. Therefore, it's much more reminiscent. Here, just notice what I was saying to Rafael, that just because you expect with something that has a mass, doesn't mean you're type 1. You really have to do the calculation in order to see into some physics argument to see dynamically relevant. Okay, so that's the just basics of this theory of critical collapse. There's more details here that wouldn't let explain. So in this talk, I'm just going to be focusing in this talk, which has apologies, I told you much.
And you have it about, we started at 350, yeah.
Okay, so
Before you continue,
Yeah.
will you say more on the analogy with the transitions?
no.
So then I ask now, like if you were to make an analogy, like for example, this transition, we can explain this game behavior because we find that the also scale there is other.
Well, this similarity that I'm explaining is the scaling variance.
But
It's you have so I'm going to show you how to do it words, but you really work with scaling variant words, and you see the cell similarity, which means there's just a scaling variant in this ecosystem.
so what is the missing variant and there's transformation? Actually, the action.
So okay, let me show you. So there, I told you there exists two types of the cell similar solutions. There was a type, and there's a continuous type. Three type is interesting because this is the thing that the chocolate found because he was dealing with numerical scalar. And as far as I know, the discrete cell similarity is something that we obtain only sort of numerical. But there's an analytically tractable set of continuously cell similar solutions, which is one thing that actually without. What does it mean? Continuous cell similarity? Well, the exact condition. This is the answer to the answer. There exists something called a homothetic kilometer. L side of G is the version of this metric, where all these coordinates here T and certain coordinates adapted to the scale. So T is like it's a small T. X is like R over T or something like that. These scalar coordinates supposed to be in scaling regime. And then if you have this sort of condition for the killing vector, then this allows you to write always the metric in the form. Where any type can then actually pull out a factor of e to the minus some factor t times this only spatially dependent. So when I was saying stuff like oh, it's almost the same on all of these scales, what I was meaning is that I was sending t to infinity, so towards the singularity, and you see that it doesn't affect it. So when g was the same on scales. And I mentioned t equals infinity. This is exactly where the name is it looks as if it's g is 0, and you can check that the ridge is similar to itself. Okay, so that's just the generic thing. In our work, we actually focus on those which have these properties. One is in 2 + 1 dimensions, one is spherical, one is in 3 + 1 dimensions. And I'm not talking about the rockets, but it's always gonna be like all of my layout are gonna be exactly the same as for the rockets, quality. Of course, it's much more quality, but so this is a classical theory for collapse. Any questions for Megan?
And is this T to infinity thing the answer to my question about vertical quantum gravity? Because you never actually get the value.
So what I'm gonna show you is that should I again ruin the punchline? We're never gonna be in the regime where we leave semi-classical regime. Yeah, we're gonna exit the regime. We're always gonna be working with T small enough. But this is already enough. We will see. To numerically that we're gonna have a different ability on it. Okay, so that was a classical story. Now what I want to do is full quantum effects. And this is really where the business comes in, because as I mentioned, there's a lot of other papers who have the first to answer quantum effects in one way or another. Some caveats with respect to all these works, and we can read all about it. So what we're gonna do here is employ the dimensional reduction and just try things at the 2D level. We will see that this actually turns out to be the cleanest analytical approach. I'll try to address all the caveats within actual reduction. Okay, dimensional reduction, I don't need to tell you all what it means. So we reduce down to two dimensions, and I obtain some sort of a branch which looks like this, that I don't make it to one point, which is this point. That matter in our case, of course, how many everybody knows this, but most people neglect it for various reasons, because sometimes it's justified, it's not. But it's crucial here that we keep track of the dilettante because it's gonna be the action plan. Okay, so now this 2D action. What we want to do, quantize the matter action. So standard quantization is through the heat kernel analysis. And this is some sort of standard technique that actually we didn't just pull out the literature, we actually did it. But in some just a couple of words, what does it mean? Heat kernel. You just take the equation and expand it as asymptotic CD expansion. And from this, of course, you have things like the but from this expansion, you take what is known as coefficients of the tree, which in our case is going to give us this. So you might be more familiar with this part, which is the formally called that. But because we had this non-developable delta. To matter, we're going to have these five here as well. Okay. And this anomaly that we obtain here is something that is purely from DOE structure. So this is something that and crucially state independent. Local, always true tackle statement about stress. It will depend on the field, but not depend on state.
And the expectation speed depend on the speed. Size is scale.
Size is a dilettante.
Sorry.
Size is certain. Yeah.
Yeah.
But that was
F.
what is it? Yeah.
Okay.
Should make phi is a dilettante. Yeah. Okay. So I showed you how to take anomaly, but obtain the same equation by basically going into the particle action, which is which I'll show you now. So variable, it's some sort of a non-local action from which we can actually get the trace anomaly. That's an equation of motion of this action. Okay. The reason why we want to do this is to obtain more information than just the trace anomaly. We want to obtain actually the stress. How I deal with non-local actions? Well, if you just look at it like this, if you include auxiliary fields, then this is how you can actually help you solve the problem. So what we do is we introduce two sets of auxiliary, two sets of these goals, chi1 and chi2. And in order to reproduce the action and the equations of motion, they have these expressions. This is all very standard. I'm just showing you because it's nice math to But if you include these auxiliary fields, then your action is going to be local and so it's a very standard form. It's all very standard form. You can fix it to match with the original. So these languages that we're determining the equation of good pi have to satisfy some basic calculations. And now that I have a local action, that means that I can just use that example definition for the stress tensor, which is just the action with respect to the metric in order to obtain stress. So the stress tensor is going to be something.
Why are you saying auxiliary kinetic?
Well, it's auxiliary field using, but when I need to read them out, I should go back to my original action. Put it on the ghostish, and this is what you're asking. But you're not any physical fields.
Actually, auxiliary field does not kinetic activity. Okay.
I mean, here what I have is just
You have equation motion.
yeah, I have
Motion which depends on.
right. So you mean like in my action here, I have a kinetic term.
Yeah. Then how low energy you go, you use it. That's same as saying, yeah, I would just be confused. I want to use auxiliary.
We're using it maybe it's, I don't remember the first time using auxiliary fields. I would just say that you use it in order to action that I started with local, and then you can just get results out of it. It gives you one shell the same results as the normal action.
I'm wondering if that's okay. It's okay.
Are you going to tackle classical quantum mechanics?
So I want to stress tensor coming out of that.
This is actually
This is the sorry.
the classical version is actually the expression. Delta gamma by delta efficiency. Or is it I going to do a quantitative or
I mean, this procedure is normally a loose effective action, so it's
Yeah.
supposed to give you the.
you're going to make this actually class.
Yeah, I'm treating it class.
Okay.
Yeah.
Then it's fine if it has variance, right? You can only fit mechanical would be a major difference. Chi1 and Chi1 are quite different.
Yeah. I should think about this.
So if you're using this action, and then you will write specific solution for the scalar field. Solve the equation of motion for the scalar field.
So let me try to remember. So scalar field source is the geometry. I will show you later on.
Yeah.
I mean, here we just write the rule
Yeah.
procedure. So that's going to have its own answer associated to it. But from this procedure, we obtain is an add-on. So to this classical stress and quantum stress tensor, which comes from
Okay, for the fluctuations of the scalar field around the class solution.
Yeah.
Right.
Any other questions?
I think maybe I can phrase the way that if you, I want to I2 dynamics. It's like auxiliary specific. Of course, you can figure it out. And there is no
Okay,
just
yeah.
and then go back to the original.
Yeah, that's good.
Exactly figure it out. But now if you do that, this will use all kinds of correction. I want to add to correction. And it won't go back to the original set, right? Because you have if you do classical integration, yes, that's of course how you design integrate, but fine, of course. So it won't go down. They could do correction associated with this. I want to kind of take it. So that's another way to say.
I'm never treating this my understanding, I'm a little bit new to this whole story, but my understanding was this non-local action for you gives you medium. So I don't have to treat it in a practical sense. I have this action that provides for me the stress tensor, which is considered to be one stress or something for quantum effects at the student dimensional level. This was my understanding of how this was supposed to go. I can do more details to just make sure this is true. What I've seen in the literature, this is how it is. So you're not putting it in the calculator.
Oh, so you're not thinking loop.
Like what I'm saying, so this stress tensor here is the quantum tensor at the 2D level. And then you can see what happens now when I go up and so forth. But
Okay, but the idea here is that if you integrate Taiwan and Kai, you get the no local action that was on the previous slide.
that's right.
And that no local action is a quantum correction around.
It captures, yeah, it's supposed to produce for you the trace anomaly.
Yeah.
Equation of motion. The procedure for the auxiliary fields actually have a full stress tensor. So the trace anomaly doesn't feel statement. Okay, and because now I have these auxiliary fields that have to satisfy second order differential equation, they're integration functions, which are basically going to be state dependent functions. Okay, so from action now, I have some new, we're gonna encode the states into, you're saying no.
It's standard to differentiate to get the stress of the Polyako action. And then the non-trace part to get at the right position to be the
Yeah, of course.
So I think that the numbers are also stated. So
No, there is difference there.
where is the state difference going? Values of 500 like nothing in this action depends on the state of scalar, right?
Nothing in this action depends on the status. Yeah, it's only when I rewrite it to this term. And then I have some freedom, basically, is the only freedom that I have is the constitution of the state.
Are you saying the zero modes of Chi1 and Chi2 are in state that they want to be?
Well, yeah, I can add whatever I1, whatever, if I1 particular, a homogeneous part of it.
So then you're changing the thing. You're not doing only action. You're doing nothing more. What I do. Right? Because imagine I have like a bump in my scalar field, say, we can move on if it's not a department. I just say, you have bump of energy that is not a zero of bumps. Okay. Cannot go into this. Maybe it's
Okay, let's do it later, because this type of formalism is, for instance, to evaluate. It's sort of a newer formalism, and like you have to take terms of some classical. People have used this to get more correct results when it comes to, say, black hole operation. I mean, let's discuss it because I yeah, here I'm just gonna do this, and then it tells us here's your system. Okay. So from here, because I obtained some stress tensor here, right? Using this anomaly, right? I can obtain a quantum stress tensor. And as I think the stress tensor is some kind of freedom now because this chi will have such this part which is these integral functions. But if it turns out that all these functions that I obtained, which were not in it, and even though there's gonna be like four of them, both regularity, and I'm gonna discuss it a little bit more. But in these examples that we've shown in the study, if you just regularity away from singularity, so for it's not regular parts of the space, then it turns out that you can completely fix the form of this stress tensor, effectively fixing the state. And why are you fixing the state? I say that because then you can check the stress tensor basically comes to cause or more better polar like features. It's gonna have spectral polarization around the center of my space, but as it goes like infinity, it's gonna die off. Simple behavior is something that is from this type of analysis. Just singularities when you fix these integration functions, and you got out and you keep state. And this is something okay, I will talk later, but this is very much into the usual where you have all sorts of states. But this particular self-system, by doing this analysis, you obtain a unique state. And when you apply it to the black hole, you don't obtain states. What I'm to say before, you obtain back. Well, you can have a choice of any kind of state. But in this particular setup, you obtain. So we thought that would be interesting. Okay. So you're very quick about it. You obtain the 2D square, but using ratio laws, basically uplift higher dimensions, then uplift this stress center to the higher scale for. Okay, so caveat with this, is this a little clear, more or less? Okay. So now that I showed you this, show you just very explicit example of solution. Just keep in mind that we're going to have the same qualitative features also for the rubber. The variable solution is some random solution that's giving price. And this n is not the dimension, it's just parameters, really it's an in parameter of these solutions. And you see that measured here 1 of g of x times e to the minus 2. The scalar field which supports the solution is this, where it is infinity, and this is stage, and now I want to use the method section in order to obtain my quantum stresses. So this is where I wanted to mention this a little more. Just by putting the regularity of the stress tensor, you fix the state to be polar with no range of infinity. And the resulting stress tensor is a little bit cumbersome. It was a calculation. But just look at it, you can denote that it's a very nice functional form. So it's such a self-similar form. Okay. So this is how the quantum that I obtained in 3 dimensions. Using conservation laws and uplift hydrogen, using this anomaly induced action, I stress tensor sorry.
So T or C is.
3D.
Oh, 3.
Because this one is 3D. Yeah, this F, mu, X, and that, just bear in mind that none of those are dimensions. It's just a function. Okay, so now we have a stress tensor, and now I can see how does it actually back react onto my geometry. So I can solve the Einstein's equations to see what is the right? It's just a simple problem. But the proper analysis of this problem really requires not only quantum effects, but also classical effects. So the stress tensor has a form like e to the t times some sort of function, and because it has this e to the t, this t goes to infinity, so as I go closer to singularity. And so we call it the quantum growing. And because this state that we obtain is symbolic, we would say that this quantum comes from some sort of vacuum polarization effects coming from this collapse in singularity. That's something that we've seen so far. But it's also important to take into account classical perturbation, because as I was telling you, this is about collapse, and spherical collapse means that if I want to see some interesting phenomena, I should move a little away from the spherical surface. So it shouldn't be electric. I should be a little bit away from it as well. You know, how is it going to lead me to black hole solution or the classical solution? This is something that accounts for by including classical perturbation. And what we want to make sure so that okay, now include these quantum effects, but is the solution still critical to include these quantum effects? This is something really okay, so by including these two effects, we obtain vector geometry, which has some sort of a very form of this type. Okay? So the zeros, the usual Garfinkel, This is a classical perturbation of what I'm on top. You see that they're telling me how I'm moving away from the solution. And this perturbation comes from following the back reaction of the quantum percent of my geometry in the new GPUs. New GPUs of this. Equation analysis, so everything here. And all these functions, F, C, R, F, Q, Y, Q, blah, blah, blah. These are all known functions, nothing so. So we have this metric, and now we want to analyze what is it thing. Because the metric that we have looks really complicated. So we would like to actually have some sort of a simple way of seeing what is it that we actually think. And to do that, we're gonna simply calculate pocket mass, which is just calculated in some way. Basically use ray tracing in order to see when we uncurrent currents. Because it's a problem that we want to solve, right? We want to see like what we actually think. The standard notation here is that we sample r squared to be equal to 0. So the conditions of the current horizon, and if it's less than 0, we have. And what can show the generic form of this now is going to have something like this. So again, these little f's are functions that are well known, and they have a very animated. Okay, so what do? We just basically plot how this looks like. First, let me note that after equations to 0, immediate back reaction already forms a horizon that's a sort of finite equal to a range. So it's already enough to see that if it's just a critical solution and just that I already moved away from the next here. Okay, I'm no longer coming to singularity. But now I want to see if the criticality is still things. So what our results really show how that reaction, what it actually does is to shift this critical parameter, star, the classical value for creating a black hole. It shows some sort of a smaller value, Q for quantum, because the black hole will form at some sort of an earlier value of P, right? Now quantum effect, so I still have, but I'm going to form a black hole at some earlier time. Sign of AD equal to P7, some people to P sub Q is smaller. Sorry, it's a lot of, I don't understand what I said. So we have, therefore we have sort of a shift in this threshold. But we see that this new behavior is preserved, but now with this new P. And now we are surprised that I spoiled at the beginning of the talk. See that we no longer have a time for space. So it's not just that we simply shift this smaller P for which now we have a negative singularity. No. Actually, what happens, type 2 actually becomes a type 1 solution. So how do we see that we have a type 1? Well, we basically plot some sort of a covariant thing, seeing in a nice way like it's competition between classical perturbations and quantum perturbations, and we plot it against them. And we see that as we're approaching the solution that we obtain is actually going to end up with a constantness. And not zero. So we're approaching a constant for the mass of the solution. The solution, as I was mentioning before, when in the semi-classical regime, so whenever in this T very large, but sort of some simple T, but we already see there that we have finite mass solution. So this is why we're saying that this solution that we obtain is a sort of this type 1 solution. It's no longer there. A lot of words. I don't know if I'm making it clear, but or make it simulate next year. Okay?
So remind me that type 1 solutions also have a universal critical exponent.
Sorry, they have.
So type 1 does have a universal critical exponent.
Type 1 solutions have universal exponents, but with respect to a different parameter. Not the different with the mass of the white hole is with the lifetime of the solid. But they're criticals. So there must be critical scaling law, and scaling.
I was just wondering if I started like T goes to criticality, goes to critical value of T, but not so close that I'm in quantum regime. would I be able to notice difference between it? Would I be able to notice if, would I be able to find your effect is happening if I'm in somebody like.
Right, then you have to, I mean, that's why we're calling this thing, because it's really plotting the relationship between the classical and the
That's
modern.
why very, very clear. They don't go back to those, we get the same behavior.
I mean, what we see is what's plotted. I mean, we have a bunch of other parts, but like, it's always coming. If you're in the regime, I mean, you're always in the close to criticality because it's zero consistent, right? So I'm not starting with some PP very low.
Yeah.
But then I'm always close to this initial surface, and I'm just seeing, okay, in evolution, with these new quantum effects included, what is the nature of this new sort of thing?
The order parameter for these phase transitions is the mass of the black hole, right? What is the thing that is controlling this gap?
Good. That's gonna be one. Of course, so there are two scales still. We should say one is small, one is large. One scale is h bar, and the other scale is exactly the scale which like the mass of the big black hole, classical collapse. So this p minus p star, including scale. Okay. So those scales that we come with, and here because I'm paying attention to the finite mass, what is the mass? Proportional to h bar, because this is exactly the thing that I'm saying. But this twist that I could do, I would why is this maybe so obviously not interesting.
So the definition of black hole, or not, it is a event horizon.
Apparently, yes.
Horizon.
Yeah. Numerically, you check the current horizon, but they always like.
Upper horizon is finite distance, right? You can approach it is huge. The finite size, right?
Well, yeah, I mean, you're just seeing for which value are you gonna create traffic for your space. Which value of R you're gonna create value. And if you don't hold that for no value of R, we will never satisfy the condition this now is clear. So if you get as you call this function, then there's existing horizon. This is how you determine whether or not you create a value. Without being told.
But I think it's okay being at the mass here, but it also it just long thing with some now or something, and it goes to the other side.
But so the critical solution that I'm here, so Mason in between, that is one that became a type of blob. So I think that's like a finite blob. But I can still create black holes. It's gonna have a start at some mass, which is meant by the gap that's provided by this.
Okay. And if it goes the other side, then eventually it's
Just lots of, yeah, this is why this is still a critical solution. So it's when we obtain these perturbations are not critical, and I didn't indeed it is, but now we just obtain some sort of solid quantum stuff, and I don't know what it is stable or not, and again, it's just has to proper analysis. This middle region, but that's. Just quickly go through the logical outline I just said. So we start with the classical continuous substance function. We then reduce it to D. We trace anomaly to the heat credit. From the anomaly, we obtain the convection, from which we can make auxiliary fields. We can obtain the full stress tensor. And finally, in back I can get the stress tensor. We see a vector metric, from which we have to negative singularity. Okay, so that's the summary of what the topic is. There's a bunch of future directions that I can take, and I'm very happy to discuss any of these. Just wanted to at the end, just maybe mention this point of the size and what is the stress shift that we're discussing, and then we can go into the other thing. Well, I will mention this. So one thing from the future. So the quantum introduced then led to two quantities that the shift. There now exists shift with the spherical threshold, and now there exists origin. We can have generality in general, like what is the determinant sign of this spherical threshold? And this is something that you can actually do doing any sort of calculation. So right now, algebraic equations can determine what determines the sign of the spherical threshold. So you can just simply, under the assumption of linear, we're going to make an ansatz for this area that we're going to evolve to see if we have an apparent coordinates or not. And as I mentioned before, it gives you some sort of a very generic form for this apparent coordinate, where all these functions are only functions of the perturbation profiles, right? Everything that we're doing. Now, how do I just well, there's a condition for the apparent horizon, there's also the radius of the apparent horizon, which will be by some sort of an externalization condition. Here, you basically think that the sign of the threshold depends solely on the sign of the perturbation profiles for the other quantum. So it doesn't depend on this condition. It doesn't depend on whether or not my stress tensor is e to the times f of x or e to the 15 t f of x or something like that. So it doesn't depend on the steepness of this growing hole. It only depends on perturbation. Okay, so that's something. And what about the mass? Mass, yeah, numerically, mass has some sort of formula that you can determine. As you get results, you can see that the mass gap, as I mentioned before, is going to be equal to some power, if you will, or in 3D is going to be basically proportional to this arc. And you see that the mass is going to be minus h1. I think so this omega q is given by d minus 2, so the Garfinkel, which is 3 dimensional, is going to be just equal to 1. In higher dimensions, is going to be equal to d minus 2. Okay, so this is a little bit unsatisfying. Telling us that the mass of the black hole that we have at the end is just going to be a very small black. It's just going to be this bar. But no, actually, the size of the black hole cares about these other functions than s, which I defined here. You see that these functions are functions of the perturbation. So there's fq, there's f0, actually just for the critical solution. There's all sorts of things coming in. And in principle, nothing is prevented from dreaming that maybe these numbers here can be big enough to make this whole maybe 7 possible. Because you have for example h bar, but then you do like 10,000, then you get 10,000 h bar, and that's already bigger than 10. Okay, so why am I talking about phenomenology? I'm talking about this because it may be interesting if you think about, for instance, spectrum of your black holes. So I'm very happy to talk about this offline right there. But just a one sentence summary is that people have looked into these primordial black holes for 30 years now, as you can see there. And one of the main mechanisms, turns out, for forming these black holes seems to involve critical collapse. It's basically because, in some sense, it gives you it prefers holes which are formed near the threshold formation. Exactly in this regime where critical phenomena actually enters. This critical collapse is relevant for black holes, then quantum corrections clearly shift the radius and shift the mass. Then you may ask, okay, no, if I look at number W, numbers here are small, and that may be the case with mass gap. But the crucial thing is that what also goes in calculation is the shift of the threshold. The reason why I mentioned the threshold is because it actually goes to the determination which of your spacetime can actually collapse black holes in some way or setup. And the crucial thing is that it comes in so I have. So even if effects modifying my threshold shift, because they haven't been actual, have an actually measurable effect in the regions that are collapsing. That was a lot of words. hope some of it. It's just to say that if these programmable black holes have reason to exist in our universe, and just for the finding, which may be more interesting to this crowd, with holographic imprints. So, where we actually used the fact that there is a self-similarity, right? Near the whenever we have the state similarity. Using this feature of self-similarity, we managed to track what is the boundary function of the space which has an similarity. So this means that we can obtain a signal of singularity. This is something that we did 5 years ago. And now the obvious question is, well, we were there, where was just classical critical collapse. Now that we have some effects, this is going to modify when we obtain a lower boundary. So the signal that we have is something that builds up. Here now we're going to have quantum effect. The question is now, is this going to change the building up nature of this observable, or is it going to make it smear it out? Is it going to make it regular, or what's going to happen when we retire boundary function? And it's actually something that's very doable. Like this calculation, we did it for any dimension. We did an empty ADS. You just put a scale in an empty ADS. Simply impose that your scale has a regularity in the center, but similar conditions. That's it. That's the actual. And then you can very easily use the extrapolate dictionary towards the boundary. So now you can just simply use everything that we have, which is explicit and see what happens and the same thing boundary. And that way you will have a signal and singularity of the boundary. And to starting point, starting also which has a natural formulation in ADS 3, so they give the natural questions. Okay, so let me just finally summarize. We studied these analytic models. Once one were added, we resolved for this precedence, and things that this is one mode bipolarization introduces a finite mass gap that you can no longer make singularity, thereby forcing cosmic censorship in quantum mechanics. Okay. Thank you.
Are there any questions? Yeah.
Can you picture what causes the neural stress tensor which acts as I understand that okay, it's like fluctuation in the scalar. Is there a way in that stand form in a more precise?
Well, I mean, my intuition is really just that it's just fluctuations on the scalar field that are inducing this shift.
Yeah, just say why it's the shift, why it's not.
Obviously, there was going to be a positive shift. You saw like the sign of the delta P. So whether or not comes a black hole sooner or later, for smaller values or for larger values of P, it's something that depends on these perturbation profiles. It turned out in 2 examples that we studied, is negative. So that we always obtain for smaller values of P. But it could have been easily another point. And I'll tell you how to give me an actual model with which I will calculate and see with respect to these LQs and C's that we develop for samples.
Yeah, I need something with this calculator energy.
Well, in as much as Casimir can study the polarization.
Yeah, maybe a good question. So if we would have opposite sign, that would not have resolved.
I mean, it's kind of weird to think about because you're then pushing away forming a black hole. I don't know what will happen in that case.
So maybe let me ask you, instead of a scalar, you have a fermion. Then I think, maybe I'm wrong, I think the flip of this action.
I don't think it's obvious, like,
Because the term instead of having 1 over the determinant, there's this minus long bet.
oh, you mean you're going always.
Yeah,
Unless it would be like minus t.
yeah.
That would just mean that the effect of bar is no longer dynamically relevant, and you would wash it out. But just intuit that sounds wrong. The imagine quantum effect relevant at small scales, right?
Shouldn't the economy actually control by central scientists for it? Both those are different.
Maybe.
I don't think this.
Oh, right.
I don't think determinative. I think.
Intuitively, I mean, I guess you don't understand it, right? Like, just small quantum effects are it's just that it's funny that you know the way it turned out. It didn't have to be one solution. It could have been just like something else. Have to preserve locality. But
Maybe I had the wrong intuition, but I thought that if the sign flipped, it would be like you ended up on the other side of the like phase diagram and you flew out to the black hole solution, but was flat space.
yeah, that's why I said like we're pushing further, you know, like
Yeah.
it still exists, but it will get larger.
Yeah.
Not be larger.
I just wanted to try something wrong with us. So the Taiwan getting the freedom is no modes of the box, two zero modes, right? But with the Lorentzian box, there are infinite number of zeros, and at the back of the envelope, the number of degrees of freedom into two harmonics is actually equal to the number of degrees of freedom stressed in circle.
Okay,
Yeah, I think that's why I was wrong.
I see, okay, good.
Yeah.
Yeah, sure.
There are questions, then we can continue.